All right, so just as a short introduction to the topic, I'll start with well-known trade-off. At high frequencies, we have extra bandwidth and therefore expect high throughput. But the propagation conditions for RF waves deteriorated, and so we have scattering loss, absorption, the small effective area of antennas, and therefore lower received power. Hence, a larger number of remote nodes will be needed, and so that adds a cost to the system. A potential solution here could be what is called intelligent reflective surfaces, or reconfigurable intelligent surfaces, or frequency selective surfaces, a whole bunch of names for them, or some people refer to them simply as meta-surfaces. And so what they do, they provide a controlled scattering pattern of, due to periodic supercells with variable size sub-wavelength scatterers. And to explain a little bit the concept here, so what we have on the right is the structure itself, and in red the supercell is shown, and its expanded view is here. So the blue is the dielectric substrate grounded with metal ground plane and a few patches of variable size. The critical parameter here is that L supercell, which determines the delta theta is the rotation for the incoming beam, the angle of rotation. And so the size of each individual patch is chosen so that to achieve a quasi-linear phase shift, since, so that's as shown in the diagram here, there is a dependence of the generated phase shift as a function of the size of the scatterer. And then another design parameter is the number of those patches over the supercell. So it's a very simple passive structure. It can be made active by changing the properties of a dielectric, applying voltage, and it can be done through liquid crystal-based solutions or varactor diodes, or what Gabriel presented is based on the antenna arrays. So another interesting question is what is the size of that reflector for practical applications? And it's some of our internal studies where we looked at the specifically for 5G applications and millimeter wave channel. The question so we introduced some sort of figure of merit, which is an average throughput based on a physical layer of a 5G 28 gigahertz channel. So we ended up with the plot shown here for figure of merit as a function of reflector size, M, which is a ratio of the linear size over the wavelength. So after some threshold, so if the scatter, that meta surface is too small, it just cannot generate enough power to generate any throughput. But after some threshold value, the growth is approximately linear with the size, and it starts to saturate when the maximum bit rate is reached for the peak reflected power. So the more details can be found in the, this upcoming paper. But so the answer to that question in the title is the larger the better, but at some point the advantage of having a larger size we will saturate with that M, which is size of the meta surface. So now what we have here is, on one hand, it's well, so we're looking for potentially controllable optimal redirection of incoming radiation and relative ease of installation, but with potentially low cost, especially for passive structures. Promising results reported in the literature. On the other hand, it's complexity of design and co-optimization of standard remote nodes with those meta-surface reflectors, especially if there are few kinds of each of those, and cost and practicality for reconfigurable surfaces. So if it's a really larger size, maybe it's just easy to add another remote node and not that more expensive structure. Loss increases and efficiency decreases in high frequencies, and so aesthetics is another thing to consider for outdoor applications. That may be okay, but not every indoor application would welcome that type of structure, like 2 feet by 2 feet hanging on the wall. So that's sort of the problem statement, and the last session of this meeting will discuss the input from both academia and industry.